In this video, I want to talk about solving problems where we're given a set of vectors from Rn and we want to know one of three things, or maybe more than one of three things. Are these vectors linearly independent? Do they span Rn? And are they a basis for Rn? And then finally, there's a question I'll look at. If you determine that a set is linearly dependent, not independent, then that means that there's a non-trivial linear combination of the vectors that gives you 0. And so in that case, if we've taken a set and determined it's linearly dependent, we want to know, well, how do we figure out what that dependence is? So there will be kind of a process here, and I'll hop back and forth between examples and how we approach these things. But I think let's start with an example. So we have three types of questions, right? Are these linearly independent? Do they span? Are they a basis? And often you have an easy answer to some of them and a hard answer to others. And what I mean by this, sometimes you can avoid calculations altogether. So if we're interested in whether something's linearly independent, if we have too many vectors, a set can't be linearly independent. I'll come back to this at the end, and if this isn't obvious why this is true. I don't think it's obvious at all, but you can hopefully convince yourself by the end of this video why this is going to be true. So if we have too many vectors, more than n, they can't be linearly independent. If we have too few vectors, we have fewer than n vectors, they can't span all of Rn. We don't have enough to get everything. And if we want a basis, we'd better have exactly n vectors. This actually follows from the first two. Right? If you're convinced that these are true and you realize that a basis is a linearly independent spanning set, then if a set has fewer than n, doesn't have more than n, and doesn't have fewer than n, it has exactly n. And then finally, I just mentioned this now, none of my examples have this, but if we're talking about linear independence, there are certain situations, these are the main two I can think of, where you immediately can see that there's linear independence. If your set contains the 0 vector, it is not linearly independent because you can create a non-trivial linear combination by just multiplying the 0 vector by 1 or something. Also, if you have a set with two identical vectors, that will not be linearly independent. Technically, a set with identical elements is called a multiset. Set's not really allowed to have copies, but we'll see later in the course that there are good reasons to allow or to want to consider sets containing identical vectors. We'll be talking about columns of matrices, and there's no reason that a matrix can't have two identical columns. So these are the easy approaches. We'll deal with the hard approaches when we get there. Let's go back to our example. So I'll address the easy ones first. So we have three vectors in R4. That means that this does not span the set does not span R4. It's too few vectors, right? To span R4, we need at least 4 vectors. And similarly, to be a basis, we would need exactly 4 vectors. So it is not a basis for R4. I don't know why I wrote 4 instead of R4. So 2 of the questions were easy. The third question is going to require more work. So how do we determine whether this is a linearly independent set? When we're trying to figure out in a harder situation, so we have a set that could be linearly independent. It's 3 vectors out of R4. That's possible. The way that we figure out whether it is linearly independent is by taking our vectors and putting them as a matrix with vectors as columns, and then converting the matrix to echelon form. That's our first step, or our first 2 steps. Put the vectors as the columns of a matrix, convert it to echelon form. Let's see what that looks like in this example. So the vectors as the columns of a matrix, that's saying that we have 1, 3, 0, minus 1, 4, 7, minus 1, 13, and minus 5, 6, 8, 6. And through some series of row operations, if you need a refresher on how to convert something to echelon form or to all the way to reduced row echelon form, this video is not the place for it. I have another video that you can watch on that. In this video, I'll skip those calculations just because otherwise it would take way too long. So we have a series of row operations, and in this case, we're trying to figure out if it's linearly independent, and once we get to echelon form, we don't actually need to go all the way to reduced row echelon form. Well, that would work as well. We can figure out whether this set of vectors is linearly independent. And what are we going to look for in our echelon form matrix? We want to look at whether there's a pivot in each column. So if each column contains a pivot, the original set of vectors is linearly independent, and if not, the original set of vectors is linearly dependent. Going back to this example, I'll circle the pivots in blue. I was hesitating between a circle and a square, and I did something that was neither. Let's go with squares. These are our pivots. And so each column has a pivot, or in other words, each column is a pivot column. And so these vectors are linearly independent because there is a pivot in each column. In echelon form. All right, so we've determined that these three vectors do not span R4, therefore they're not a basis, but they are linearly independent. Let's go to another example. And again, we're going to answer the easy questions first. So we have these four vectors here from R3. These vectors are not linearly independent. There are too many. Similarly, they're definitely not a basis. Every basis of R3 contains 3 elements. So again, there's too many. But they might span R3 and they might not span R3. We have to check though. We can't be sure. So how do we figure out whether they span R3? Well, let's go back to our document. This is one of the harder problems. We still start with the same thing. We're going to create a matrix with the vectors as columns and convert the matrix to echelon form. So all of these harder steps, when we're trying to figure out one of the harder questions, they all start the same way, which is really nice. It means that we don't have to do lots of different things. Okay, so we're going to put these vectors as the columns of a matrix. And we are going to convert this matrix into echelon form of some sort. It could be reduced row echelon form. So we'll have a series of row operations. And in this case, I converted it all the way to reduced row echelon form just because I want that later, but this is not really necessary to answer the question we're answering right now. That's a 9 there. That's 9 halves. Let's write that in a more readable way. So this is what we get. And the way we use this is similar, but to when we were working with linear independence, but we're looking at the rows now. If the echelon form has a pivot in each row, then the original set of vectors spans Rn, and if not, it doesn't span Rn. So going back here, our pivots are here, and we have a pivot in each row. So this spans R3 since there is a pivot in each row. And I just want to point out, again, there's a reason I took this all the way to reduced row echelon form, but it's not to answer this question. Right? Once you get a matrix, going back to our other example, once a matrix is in echelon form, all of the additional steps that you do to get it to reduced row echelon form, getting rid of the fact that these aren't ones, right? Like dividing by -5, dividing by -19, and then getting rid of these things here, they don't change where the pivots are. So when you get to echelon form, you already know where the pivots are, and usually there's no reason to continue working. You could take it all the way to reduced row echelon form. For instance, if you're using software to calculate it, maybe you just have it set up so that you get reduced row echelon form, but usually that's not necessary. Okay, so we've done 2 examples. Let's do a third. And this will be my last example. Don't worry, there's not some crazy number. So here we have 3 vectors from R3. In this sort of case, there are going to be no easy problems. What I mean by that is that when you have 3 vectors from R3, they could be linearly independent or they might not be. They could span R3 or they might not. They could be a basis or they might not be. And so we'll have to answer all 3 of the questions. But as I mentioned earlier, the nice thing is that to answer all 3 questions, we always start the same way. And the hard part is doing that, is the conversion to echelon form. And then we can just figure from our conversion, we can figure out what the answer to each of the questions is without any more calculation. So we're going to do that. We're going to put these vectors as the columns of a matrix. We are going to convert this to echelon form through a series of row operations. And we end up getting this. And again, we're going to evaluate where the pivots are. The locations of the pivots are going to determine whether we have a linearly independent set, whether it spans R3, and whether it's a basis. So let's answer the 2 that we already know how to do. So we have a pivot in each column, right? So this set is linearly independent. We have a pivot in each row. So it spans Rn, or in this case, R3. How do we figure out if it's a basis? There's kind of 2 answers to that question. Let's go back to the document. In the document, it says, well, you need a pivot in each row and each column. And if that's not the case, then it's not a basis. So in this example, we do have a pivot in each row and each column. Pivot in each row, pivot in each column, and so this is a basis. Another way to look at this is that once you've determined that this thing is linearly independent and that it spans R3, that's the definition of being a basis. Right? So if we didn't want to separately evaluate that, we could do this. But if all we were worried about was, is this a basis, we could just jump right ahead to, is there a pivot in each row and each column? Okay, so I want to look at a few things here. So first of all, we had some easy answers to the other problems, but I want to show you that we could have answered them using the reduced row echelon form as well. Right, so we didn't need to check whether this spanned R4 using anything fancy because there were only 3 vectors. But if we had, we would notice that there's not a pivot in this row. So this does not span R4. Similarly, if we were checking if it's a basis for R4, we don't need to go to echelon form, but we notice there's not a pivot in this row. So it doesn't have a pivot in each row and each column. Similarly here, if we were using the echelon form to check if it's linearly independent, we have a column without any pivots, right? So that's another way to see that it's not linearly independent. And so we could answer these easier problems using the harder problems. This method also explains kind of why the easy approaches work. So if I look to these back to these easy problems, if I said I would come back to this, why is it that more than n vectors in Rn can't be linearly independent? Well, going back to this example, I don't even need to know, I don't need to see the echelon form to know that there won't be a pivot in each column. If you think about the method of converting a matrix to echelon form, you can only end up with one pivot in every row. And I only have 3 rows. So I can look at this matrix and say there's going to be at most 3 pivots. There's 4 columns. There's no way there can be a pivot in each column. Similarly, a set of fewer than n vectors cannot span Rn. We can see this in our first example. I don't need to convert this matrix to echelon form in order to see that this matrix, when it goes to echelon form, cannot have a pivot in each row. Because it can only have at most 1 pivot in each column. There's only 3 columns. So all I could possibly get are 3 pivots that can't have 1 in each row. And the same idea is true for a basis. Once we've determined that to be linearly independent, you need n or fewer vectors, and to be spanning, you need n or more vectors, then a basis has to have exactly n vectors. So the easier problems actually follow from these harder problems. I want to address one last type of problem, which piggybacks off of what we're looking at not right now, what we were looking at in example 2. This set is not linearly independent, and so there's this natural question: what is a non-trivial linear combination of these vectors that gives us 0? And so to do this, how would I solve a non-trivial linear combination? Well, I would set up this equation. I don't know why I wrote that as a single 0. That's not wrong, but let's write it out as the 0 vector. I want A, B, C, and D such that this is true, and I want them to not all be 0, right? I know that if I make all coefficients 0, I'll make this true. And so how do I solve this? Well, I would create an augmented matrix. And through a series of row operations, I would convert it into reduced row echelon form. And you should notice that, Oh, I wrote it down wrong before. It was minus 9 halves. It didn't affect that answer, but it will affect this answer. I got so caught up in the fact that my 9s looked terrible that I got distracted. And notice what happens here is that when I try to solve this system, on the left, I get the same thing as if I hadn't written the zeros in the first place. Which makes sense, because when you look at the process for converting to reduced row echelon form, you're working left to right. And so the only non-zero entries you ever deal with are in the left half of the augmented matrix, because the right column is all zeros. And so to kind of summarize this, if I had already gone through and done this process, I don't need to do any more work. I know what this is going to look like when I convert it to reduced row echelon form. It's not going to change what's in the left side, and row operations never change zeros, right? Columns of zeros, multiplying, switching, adding multiples, it's all just zero, right? Nothing will ever change. And so I can take this and I can say, look, I know what the solutions are to this. Right? The set of solutions to this is, well, we have x1. If these are our variables, x1, x2, x3, and x4, x4 is a free variable, right? So we'll call it s. x3 is 9 halves s. x2 is minus 9s. And x1 is 5s. Or as a vector, this is what our solution is. And why was I calling these things x1 and x2? I forgot what I was doing. I already named these a, b, c, and d, didn't I? I convinced myself that I hadn't named my coefficients, but I had. This has happened to us before. Let's take a step back. What are we trying to do here? We're trying to find an answer to this system. And before, this happened to us when we were trying to see if something was in the span of a set. And we found an answer, but it was an infinite system or an infinite solution set. So we said, well, okay, we almost have too much here, right? We want just one answer, and we were given an infinite number. And if you remember in that video, what I did was I set our parameter s equal to 0. But we can't do that here. If you set s equal to 0, you're going to get 0, 0, 0, 0. So we can't set s equal to 0 just because that gives us a trivial linear combination. We already knew that was a solution. That's not why we did this. Usually I set parameters equal to 0 if that makes sense, because it's easier, right? Computationally, you're just multiplying by 0. So here actually what we want to do is we want to set s equal to anything else. I'll choose s equals 1, because why not? And so now we have a is 5, b is minus 9, c is 9 halves, and d is 1. Or in other words, if I go back up and write this in here, you can verify that this is true. What was my solution again? 5 minus 9, 9 halves 1. So this is a non-trivial linear combination of these vectors that gives us 0. And if you want, you can go through and confirm coordinate by coordinate that this is true. All right, so I've covered how to do all of the problems that I wanted to cover involving linear independence, span, and basis. Right, we have this category of 3 questions. You know, we're given some set of vectors, and we say, look, tell me, are these linearly independent? Do they span R3 in this case? Are they a basis for R3? We have this approach for how to solve this. We check the easy methods, and for anything we're trying to determine that's not easy, that is, that there's not some straightforward reason that it can't possibly be true, we have to do this harder approach, which isn't too bad, but we have to take our vectors, make them the columns of a matrix, convert them to echelon form, and then check where pivots are. I've covered how to do the problems. I want to talk about why this works. And so, depending on where you're at with this, you may just not want to watch the rest of this video. I think it's worth watching once because it's useful to at least at some point have seen why this works. And it's not too long of an explanation. I'm not going to do any sort of crazy, formal mathematical proof. I just want to justify, why does this approach work, right? It seems somewhat magical, and I think it's nice to see why it works. Okay, so let's look at the linear independence situation, because we already kind of did this. So if we're trying to figure out whether these vectors are linearly independent, I'm showing the wrong screen. Let's go back. Yeah. So if we're trying to figure out whether these vectors are linearly independent, the way we do that is we set up an equation. I knew I shouldn't have erased those variables. It's always bad form to do, and it's for a good reason. So we set up this system, right? If we're trying to figure out if these things are linearly independent, these 4 vectors, we set up this system, we turn it into an augmented matrix, we do row operations, and we get to echelon form. Here's the thing. Setting up this system and then turning it into an augmented matrix is the same as putting the vectors as the columns of the matrix. So that's why we put the vectors in as the columns of the matrix, because that's what happens when you set up this vector equation. We then convert to echelon form, and that doesn't affect the right-hand side, as I said before. This is all just zeros. We always get solutions, because you can't get a contradiction. You can't get an inconsistent system when everything on the right is zeros. When do you get infinitely many solutions? You get infinitely many solutions when you have a free variable, when you have a column without a pivot. And so if there's a column without a pivot, you're going to have a non-trivial solution. You're going to have a solution where you can plug in a value for your parameter or parameters and get something that's not all zeros. They'll be linearly independent. You'll only have a trivial solution if you don't have any free variables, which corresponds to, in this left-hand side, the augmented matrix, or of the augmented matrix, the reduced row echelon form of the matrix you got from making the vectors the columns, if you have pivots in each column. So that's why this linear independence method works. It's because really what we're doing here, when we do this whole process of converting or putting the matrix together and converting to echelon form or reduced row echelon form, is we're solving a homogeneous system. And whether the vectors are linearly independent is all about how many solutions the homogeneous system has. All right, so I want to justify why the span approach works. And it's actually really similar. And so I don't want to keep rewriting over the same stuff. Yeah, this is kind of a bad example. So let's go to the third example. So we want to know whether these vectors span. I wrote something down here wrong. That's fine, but I want to copy it correctly. So if we want to know whether these vectors span R3, what we're going to do is we're going to, sorry, trying to make sure that I have this all set up. We want to know whether these vectors span R3. And so the way to do that would be to set up this equation. If we didn't have this system, I guess is what I'm saying, we would set up this equation and we would say, look, what I want to be able to do is I want to be able to add together multiples of these vectors and get anything. And so we would convert this to an augmented matrix and say, all right, well, what does this look like? It looks like this. And this is already intimidating. I don't want to have to solve this thing. But what you realize is that what's going to happen is you're going to try to solve this. You're going to do some row ops. And your concern is that you're eventually going to get a row of zeros and something that's not zero. But here's the thing. That's not going to happen because we're going to get, this is the echelon form that I wrote down. And who knows what we're going to get over here. But this is what's going to happen because all of my row operations that I'm performing are determined by what's over here on the left-hand side. And this is what we get when we convert the left-hand side to echelon form. Now, what are we going to get over here? I don't know. We're going to get some nonsense that's going to depend on the original vector that we were looking for. But the point is that no matter what was here, we're going to have a solution when we get here because we aren't going to get a row of zeros on the left. And conversely, if we did get a row of zeros, like let's say this wasn't a 57, this was a 0, the only way for that to all work out is if you also have a 0 over here. But here's the thing, we want this to be true for any x, y, and z. And if you have a situation where you do get a row of zeros on the left and you're letting the whole right side be anything, some values for x, y, and z are going to make the right side non-zero in this position. And so checking whether it's spanning, the reason that we're converting to echelon form is we're trying to solve this arbitrary system, arbitrary in the sense that it can give us any vector, in this case from R3, and we're trying to see whether that has solutions in all cases. And so really what we're concerned with is there a row of zeros? Or in other words, in echelon form, do we get a pivot in each row? Okay, so hopefully that explanation gave some sort of intuition, even if it didn't make 100% of sense, as to why this works. The nice thing is you don't actually need to remember exactly why it works in order to use it, but it is nice to have this notion in the back of your head of like, all right, this has something to do with solving systems, right? It's not just some magical process. It's just that putting vectors into the columns of a matrix is what you do when you set up a vector equation and turn it to an augmented matrix. And really spanning and linear independence are statements about vector equations and whether solutions exist in certain situations.